thank you for the organizers for organizing this conference in such a pretty place and also inviting me. It's a really pleasure to be here to celebrate Roger and Sylvia's birthdays, right? Because it should be plural, I guess, 2 different days that you were born. I just want to say the first time I think I remember meeting Roger and Sylvia was at a conference in Urbana, Illinois. And I don't really remember Roger. He was probably there. And then, but I remember Sylvia. Afterwards, we were all sitting there either after the party or during the conference in the room. And Sylvia was saying, this is a conference in Urbana. They used to have the Midwest conference that went around Purdue and Urbana and Michigan and maybe something else. I do not know. And then Sylvia told, I can't remember who it was, whether it is Robert Fossum or Graham Evans. I do not know which was the 3 people were sitting, that we would like to host this. I can't really do a perfect way of Sylvia saying it. We would like to host this in Nebraska next year or something like that. And then it seemed to me, anyway, I had just graduated. I'd just come to watching this, right, that they seemed to be not very receptive. They seemed like, you're Nebraska, we are Midwest. It really isn't. I don't know what it is they were thinking of, because I had just come from the East Coast. I thought that may be what they were. And then 2 years later, they had the Midwest Great Plains Workshop that started, so that including Midwest, and then also, I guess that's what made it Great Plains, I think, that you had with, I'm not so sure, that was Nebraska, Missouri, and maybe Kansas, I think, whatever was the Midwest and Great Plains. And that kind of shows, she wants to be inclusive and is very pleasant and nicely asking, and if it doesn't work, I don't know whether it was Sylvia or Roger, somehow they made it happen in the right way. So I guess you look very surprised.
Well, I don't quite remember it, but I think that when we had the conference, we also included Chicago and Illinois.
That could have been. Yeah, I don't know what's in that Midwest Great Plains was, because I didn't know when it first started. In '89, when I first came to Missouri, it was in Missouri, which was part of the Midwest Great Plains. And the time I saw this conference in Illinois I would have thought it should be '87. So that was just maybe a year later you guys get going then. That's even faster.
That would be a good way to introduce the fact that Commutative is at Nebraska.
Yeah, that's right. Yeah, that's another conference that started. Okay, yeah, September 20th? Okay, the Commutative is another regional algebra conference within KU for Kansas and MU for Missouri and NU for Nebraska. And this year it is in Nebraska back. And September 20th. And as Sylvia says, everybody is invited and invited to their house for the party afterwards. That's what I was told. Okay, thank you. So I'm going to be talking on semigroup rings. So a little bit in the beginning, I just want to introduce the notations, even if people all know about it. So for me, the N denotes the natural numbers, which includes 0 for the semigroup. And, well, sometimes people think semigroups don't have units, but anyway, I want to have the 0. And Z is the integers. And then if you take N to the N, it's a kind of an interesting notation. But anyway, a lot of what I'm got into this is joint work with Philip Gimenez from Valladolid. He likes that N to the N, maybe. So we just put that. It's only harder to say it, not hard when you see it. So N to the N is a semigroup, which is like Z to the N is a semigroup under addition. So the way it is if you take a matrix A, this is just a connection between several different fields where the semigroup shows up. So A is a matrix of non-negative integers. Then you can think of the columns as elements in the semigroup of N to the M, because it's an M by N matrix. And we will denote the semigroup generated by them like the way we used to do for the groups. Just put that bracket. Now for us, it only means semigroup, not a group. So the semigroup, that's a semigroup defined by the matrix A. Now multiplication by, another way to look at it, is when you take the multiplication by A and just denote it by nu times A, then it is a group homomorphism from Zn to Zm and a semigroup homomorphism from Nn to Nm. It does both, right? And the image is precisely the semigroup that we put down with the A. Okay? So the semigroup, I just say semigroup A to denote both the matrix A, the set of vectors A, and the semigroup A, because it's kind of hard when you talk about it. So nu A is a group homomorphism. Its kernel is a subgroup, we know. And A and D times A, if I multiply everybody by D in A by D, they have isomorphic semigroups, because multiplication by D is an isomorphism. Then we may have one-to-one map, that's what I mean. So, but it's isomorphic to the image. We may assume there is no common factor amongst all the AIJs. It's just an inconvenience when there is one to divide by it. So the semigroup ring now is a ring over a field K, where it is, if I take that A, if a semigroup A, then it is all the products of Ti to the Bi, and which is where B1, B2, Bm is the vector that is in the semigroup A. So the semigroup ring, which I'm going to denote as K of A, is a subring of K adjoint T1, T2, Tm. So it's that's what is going to be the semigroup ring associated to the matrix A for me, okay, which will be called K adjoint A. So I just write it back because it is, anyway, you can't see what was in the previous one, so I put it up there, K adjoint A. So K is a subring and of the polynomial ring, and therefore it's an integral domain. And its dimension is therefore less than or equal to m, because the dimension of that polynomial ring is equal to m. It's also simply, you can also think of it as, which we will think of it, as the image of the ring homomorphism, which goes from the polynomial ring. I'm going to write them as x1 up to xn, where each xj goes to the product of Ti to Aij. Okay. So that's a ring homomorphism, and its image is the semigroup ring, and its kernel is the ideal I with a subscript A. That's just my notation. And then, so Ka is just the polynomial ring modulo the ideal. Right? So we've got a polynomial ring modulo the ideal. Or one other thing about the ideal, it's not so very hard, but we could show that one could just do that, that this ideal is a binomial ideal, that it is generated by binomials. And that's an interesting set, we will see. One more thing to tie these two before we move on. So the kernel of phi, the phi is the, what did I call it? I called it phi A. I just dropped the A, the same matrix A, is in one-to-one correspondence with the binomials in IA, which are important, because if I'm looking for minimal generating set of IA, since it's a binomial ideal, I'm looking for binomials. And so that whenever you just take A times x equals 0, and I'm looking for the solution, the integral solution of A times x equals 0, they are in one-to-one correspondence to the binomials in the ideal. So that's the kind of connection between solving various equations with integer solution for A times x equals 0 and this semigroup ring. So the main problem that we want to do is to find, since I've written that as a polynomial ring modulo an ideal, I want to find a free resolution for our moda A. Usually when we write it, that one has to give all kinds of reasons as to why it is, but I'm not giving anything now. I'm just saying I want to find resolutions because that's what I do. So this is really what I have been doing for a long time, so not for this particular one, just like to write resolutions for R mod i's or various other modules over and write free resolutions, just like Dave Jorgensen was talking about projectively quasi-resolution this morning. These are just going to be the free resolutions, and that is really what I am going to do. Okay. So this is a minimal, because we call such a resolution minimal if, of course, there isn't an extraneous component in the FIs, the capital FIs. That is, if the images are contained in the maximal ideal times Fi minus 1. Or if you mod out by the irrelevant maximal ideal, everybody becomes 0. So you get a free module out of the free complex. Right? The direct sum of Fi is free when you mod out by, when you tensor with R mod m. Anyway, that's why we look for minimal free resolutions. Okay. Since it's we also can make it a graded resolution by giving these xi's I think I jumped ahead. Okay, all right. Okay, I think I missed something here somehow. What I want to do, even though all of this will make sense, for just convenience, I'm not really taking this big matrix A. We'll come back to it later on. I just want one row and n column. So instead of being in this n, I want to be just integers, n. So that's dimension 1. Okay? For me now, going to be this, I'll write it down. So the semigroup now, I'm just not, this A is just A1 up to AN. It could be this capital A, the block letter A, where there could be columns, but I'm just going to look at it like that. Okay, so this is just a convenience in looking at it. And when this happens, this A, and then remember, none of these guys have anything in common because they are relatively prime. We've decided to cancel out the common factor. So such an A, which is contained in N, also has a name. This is called a numerical semigroup. And then this ring then is called, well, numerical semigroup ring. Just for now, I may not actually use the word numerical in the things. It's just semigroup. Numerical just means that dimension is 1. Okay. So that's why I'm setting the degree of xi equals ai. So I could make it as a graded, these ai's, so that I can make it, I could get graded Betty numbers if I wanted to. And if you want to kind of think of it as star, then this bi's, the rank of the those modules fi are the dimension of the tar modules. And then the bij, which would be the jth part, the degree part of tar I of R mod I ak, then those are the graded Betty numbers. So those are the numerical information that you get out of the free resolution. Okay, so since the problem is to construct resolutions, let's get going with it. The first one is when n equals 2, there's only 2 numbers. There's only one generator. So it's a complete intersection of height 1. And we have the resolution, which is the Koszul complex, right? That you started some other time that you heard from Sean's favorite complex. So R and R mod IA. If n equals 3, this is a problem that's completely solved by, this was in Jürgen Herzog's thesis, I think. So if you have 3 numbers, then 2 of these have a common factor. And in that case, a D, if those 2 guys have a common factor, and then the third one is in the new semigroup generated by the A by D and B by D, then A is a complete intersection, has these 2 generators. It's height 2 and complete intersection. What more do we need to know about the resolution? We know everything. So, and then we go on, well, there is an otherwise, that's everything else. If it is not one of these, that is, if either nobody has a common factor, or if 2 guys have a common factor, but the third guy is not in the semigroup generated by them. Then it is generated by exactly 3 elements, which are really the 2 by 2 minus of a 2 by 3 matrix, because they have to be, they are height 2, Cohn-Macaulay, and that's what you have to be. It has 3 generators. So in either case, we know the resolution and everything about it. So we go on. There's something of, not a whole lot is known in general for when you go on to n equals 4. When I say in general, that means, for n equals 4, these are the kinds of resolutions you can have. No such theorem. Okay? But in fact, actually, this is somewhat a general n. The best for resolution is this case that some years ago I did with Indranath Sen-Gupta and Philip Jimenez. And it says that if you have those things very special, A1, A2, AN is an arithmetic sequence. There's only 2 pieces of information, the first one and the common difference, right? Just like the 3. So in that case, you can have the complete minimal resolution. And it was kind of a surprising thing that it could be done. The resolution is really an iterated, several iterations of the mapping cone, and each one gives me a resolution along the way for another Cohn-Macaulay algebra, which is not a numerical semigroup ring, but a Cohn-Macaulay algebra. So it's complicated, and that's not the one I want to talk about today anyway. So because we will want to say something more general case. So in general, just if you just took every n, we still don't know how to write the resolution for this in general. So, and this is even after today, this will still be the best. But today I'm going to tell about some other classes of things for which I could write the resolution. And that starts with this concept of gluing, or different names of it. So if you take it's kind of an attempt to generalize this case of Jürgen Herzog's result, I think. Because I wasn't there in 1974 to know why they did it. But this is what I think it is. So, because it looks like it, see. If A and B, C, I write it as K1 times A, disjoint union K2 times B, where A and B are 2 minimal generating sets for 2 semigroups. K1 and K2 has to be relatively prime. If they are not, we'll divide out by the factor. So they would be anyway relatively prime. So, and K1 is, this is the important part. K1 is in the semigroup generated by B, but not in B, of course. And K2 is in the semigroup generated by A, but not in A. The reason we have to avoid K1 being in B and K2 being in A is because we want this union to be both the disjoint, that's done, and the minimal generating set for C. Right? We don't want any redundant elements there. So when this occurs, C is, we also say this is how actually first it was. This gluing came a little later. We decompose C as something times A union something times B. And K1A has the same, as a semigroup is isomorphic to A, and K2B is a semigroup isomorphic to B. So C decomposes as A and B. Okay. So the notion of decomposition of minimal generating set, it appears in the paper by Delorme in 1974, and it is used to characterize the complete intersection numerical semigroups, just direct generalization of the first part of Herzog's result. In 1980, Rosales introduced the concept of gluing for finitely generated numerical semigroups of an n, a generalization of this in some sense. And then for the numerical semigroups, that gluing coincided with the decomposition that we talked about for Delorme. So I'll write a little more. So what he proved in the 1974 paper is that if C is a complete intersection, it decomposes K1A union K2B, where both A and B are also complete intersection. And further, a symmetric semigroup is a semigroup whose semigroup ring is Gorenstein. Okay? So for those cases, he also showed that if it did decompose, then this is symmetric if and only if these two guys are symmetric, the paths. Of course, that does not mean everybody who is symmetric are obtained like this, unlike complete intersection. In this case, like these two guys are symmetric, and they cannot be written as they are indecomposable. So they could still be symmetric, whereas there's no such a thing for a complete intersection. Anyway, so using, why did I say they are indecomposable? It's because, you see, the arithmetic sequences are going to be indecomposable. The only way that they are decomposable is if n equals 3 and it is a complete intersection. It's just a simple computation for maybe, your elementary school, if we had all the words in it. So you can tell that this has to be, that's the reason why those guys are indecomposable. So for every n bigger than or equal to 4, there exists indecomposable numerical subgroups of embedding dimension n and type T. So indecomposable ones are so much numerous, and for which I don't know how to write resolution. So I'm going to write the resolutions then. I came too close, huh? Going to write the resolutions. So this is the time to know, only for decomposable ones. So I call resolutions of glued semigroups. So before I state the theorem, I have to have a whole bunch of sentences to say. So I write C like this, and then A will have now some P elements that generate A, and B will have Q elements. So KA will have x1 up to xp mod IA. KB is y1 up to yq mod IB. Then the ring of A will have x's in it. Ring of B will have y's in it. And then ring of C is going to have x and y, and then its ideal is IC. Right? That ring RC is just that RA tensor RB. So C being a gluing in terms of the minimal generating set of IC is going to be required. So these are some easy observations. The first one is if A and B are numerically independent. That means that there is no redundancy in the number of, they are minimal generating sets for their semigroups. Then C is a minimal generating set. That's why we picked K1 being in the semigroup generated by A, but not in A, and so on. Since K1 is in the semigroup generated by B and K2 is in A, there exists non-negative integer that I can write it like this. K1 is something times Bj, K2 is something times A. IC is minimally generated. This is something it requires a proof. I'm just calling it a fact. That's because it can be proved and not be done today. So it's not very much to show. So it's minimally generated by IA and IB and exactly one other element that looks like this. The reason it is in purple is not because it's supposed to be purple. It may not look like that. The reason it is in that is not that I'm not proving it. It is easy to prove, is that this is the definition of gluing that Rosales had, which happens to be the same as the decomposition of Delaunay. And we will use that, come back to it later on. Okay. So rho is homogeneous of degree K1 and K2 and gives to each variable in R the corresponding weight. That is K1A, K1AP, K2B1, K2BQ. Then this has weight K1, K2. Okay, now we have the resolution of the glued semigroup ring K join C. So I take the resolution of A, resolution of B, I tensor it, I get a resolution of this guy, which is not anybody we want, but it is a resolution of something. It's exactly, it resolves somebody, and that's that. And then the minimal resolution of K join C is obtained as a mapping cone of this. It's the same complex here, FA tensor FB and FA tensor FB. I'm just multiplying it by this row that I have extra. And I take the mapping cone, and that's really the resolution. It's very simply done once you see that that's what it's going to be. So that's the resolution and it is minimal because everybody around is minimal, and rho is something that is in M, right, the maximal ideal. So in particular, this is also true, right, that if I take this colon ideal, it has to be all of it, otherwise it will not be a resolution. Okay, so this is how we get a resolution for something that is glued. And this here's an example I gave apparently, so let's go through that. So see that all things that are decomposing and glued, they have really big numbers because I have to multiply by K1 and multiply by K2 and put them together, right, so it's big. So there it is. Even though I started with something that might seem small, I have the big number here. And so this is with 4 elements and 3 elements. And then I write the resolution of first one It happens to be a Gorenstein one, and so it looks like this, R mod 1. And then the second one, it's just height 2, and I happen to know the numbers, so I could write them down. So you tensor them, and that's this one comes, and then we take the mapping cone. It looks like this. I just didn't write all the maps because it's going to take a lot of time, space for me. So it is possible for us to do, and if you put it into the computer, it will tell you all those matrices and in a small space to write. So that's a mapping cone construction. So let's quickly go over some of the consequences, which is usually what you can get when you write down a free resolution, other than the satisfaction of having seen that you have a resolution. Now, Betti numbers, I can get a formula for the Betti number of C, which looks like this. And then, of course, you look at it and say, there's nothing to, this side has no C, so I switch A by B, I'm going to get the same thing. And it is really the same thing. It should be. So these two things are the formula for the Betti numbers of the resolution C. Now, type of a numerical semigroups, they also have from the semigroup language, there is a notion of a type. And of course, we have a notion of a type from doing homological algebra. That's a Cohen-Macaulay type. And they coincide, it turns out. They are the same numbers, which is just a little bit to check, but it is the same. And here is a thing that comes out of as a consequence. The type of the C is a product of the types, A and B. This formula also was independently obtained by Nari, who is in his PhD thesis, who is recently a student of Keiichi Watanabe. And it's a Gorenstein. If it is, KC is Gorenstein, or a complete intersection, if and only if both of them are Gorenstein. This is recovering Delorme's result, right? This is something he had. He had both directions for complete intersection, but this only does the direction for Gorenstein and complete intersection one way. Now, if neither of them are Gorenstein, then the Cohen-Macaulay, the KC cannot be prime, right, because of the product. You can just play with this product any times and write all kinds of interesting things that you can say. Now, you can also get a formula for the graded Betti numbers, which doesn't look perhaps pretty in some eyes, right? It's depending on that. Some people think like writing things like this is very pretty, so in that case it is some formula for BIJC. And this one, I just wanted to check the formula, and we had to write it all down for a C, and it, especially this one, which looked kind of wondered in the beginning when we first got it. These two guys have to be the same. Are they really the same? Because they certainly are different things when you look at the right-hand side. But you could check. It was the first one that we just wrote down to check. Yeah, they all work out. And this is the example for that reason. And otherwise, it may not be very illuminating. So the next thing is a lot of people are interested in regularity of things. Regularity of C can be written in terms of the regularity of A and B like this. This is just a formula for the regularity, which is people. And people are also interested in the Hilbert series, which is because otherwise, why would I have this graded Betti numbers? And that gives me the Hilbert series. But then when you do the Hilbert series, a lot of things cancel out, and it becomes a very pretty formula. And this is also a formula that Nari had. They using just semigroup theory and not commutative algebra in this sense, but it also comes to the same formula. Oh, one more thing is that if the resolution, this notion when you mod out by M, I said everybody becomes 0, so you get a free module. So you can talk about having an algebra structure on it, just like there is one for the Koszul complex, a differential graded algebra. So if F has a differential graded algebra and behave like Koszul complex, say, then it's called, it admits a DG algebra structure. So if the minimal free resolutions of A and B admit a differential graded algebra structure, then C actually inherits the structure from that of A and B. By that, I mean, we can write, once you have a multiplication, say M of A and M of B or something, I can write the multiplication for the resolution of K adjoins C in terms of that. Okay. All right. So that's, I think, yeah, I'm going to just drop now the numerical semigroup and want to see what it is that we can say if you move on from, this is it really, for n, there is not a whole lot more that I know to say as far as finding the resolution. There are some other kinds of open problems that I had a sheet of to tell if you are interested in, if this somehow so far makes you think, hey, this numerical semigroup thing seems like an easy thing, and why don't I start working on it, which is good. And there are a couple of things that are actually still from a long time ago unsolved. For instance, when you do this symmetric ones, the Gorenstein numerical semigroups rings, like we did in the example, which is not, I didn't do it today, but if Gorenstein and height 3 are always special. So if it is height 3, that is 4 elements, n equals 4, then we know it's either a complete intersection or it has 5 generators in the numerical semigroup rings. So after that, we don't know. We don't even know if the number of generators is bounded. That is, if I have n elements and I know it is Gorenstein, can you say the total number of minimal generators for it is 7 raised to n or something like that? It doesn't matter what it is, how big it is. We don't know that it is bounded. Whereas in general, of course, from n for 4, we know that it could be unbounded by the result of Brzezinski. But for Gorenstein, it's an unsolved problem to know whether it is bounded or not, and several other things that are kind of interesting questions in dimension 1. But let me go on and talk about what happens since I started with the matrix A. So now 2 subsets. So these guys are now going to be things that we think of as elements in NN, like a matrix now, A and B are. So those are 2 subsets in NN with the corresponding semigroups A and B, and the semigroup rings K adjoint A, just the same way. And we say C is like so with a semigroup ring, and it is a gluing if the ideal of C is generated. That was that purple thing that we had. It's exactly the same thing, one of those things, IA plus IB and rho, where rho looks like that because of the way it comes. Everything that is in X and Y. In fact, if you know there is only one row, it will look like that. So that's a different thing. But so if you even know the number of generators for minimal generators for IC is the number of minimal generators for A, minimal generators for B, and 1, then it will look like that. So this is a that's something to show. This is the definition of Rosales and before the gluing in higher dimension, as it's called. So when this happens, that is, when IC is IA plus IB plus rho, we will say A and B can be glued. In fact, it's a little bit loose. We may also say A and B can be glued if instead of C being A union B, I don't know why I put this, these brackets shouldn't be there, huh? Well, because it's, I meant to say C equals A, B, like that, right? It's not the semigroup. The C is the matrix. So I could also have it multiplied by K1 and K2, and this will be good too. So, and K1A is isomorphic to A, and that's really what I wanted to say. Then we say it is a gluing. I wonder if I have an example. Oh, no. Okay, the next thing I want to say is that when is a gluing possible? Like, you know, for the numerical semigroups, we just didn't even ask that question because the reason for that is in 1974, you had the decomposition from Delorme, and then 1980, there is a gluing. So you already know it was there, so you wouldn't ask when it will be there. So now we are asking when can it be. So we also, so there's another notation, I guess. So if this is a subset of an N, the dimension of the semigroup ring, K joint A, is really the rank of the matrix A. And so if the rank of A is less than N, the number of columns, then we can actually embed it in one less. You could just get rid of one of the rows nicely. That is to say, you know, don't go to rational numbers or anything like that. We could still get rid of them. And then we will be able to say it is, then it is degenerate. So if you say A is a non-degenerate semigroup ring in NN, that the dimension of the semigroup ring is n, or the rank of the matrix is n. So that numerical semigroups are all non-degenerate, so that problem doesn't occur. So for n, here's something I called it a theorem because it looks prettier. So if n is bigger than or equal to 2, two non-degenerate Cohen-Macaulay semigroups cannot be glued. So the reason I put that in is somehow one would like to see, oh no, something can't be done. Why? So that's the reason for it. But so it's a direct consequence of this theorem. I mean, the amounts, one of the trivial consequences perhaps, but there it is. It looks more biting. So I take the minimum, so we see it's exactly the same resolution because you go over that paper that we had in the writing the resolution. There really wasn't anything about n to the 1. Everything goes through to n to the n. And so this is the theorem for nn. So FA tensor FB is a minimal graded free resolution, and this is the minimal resolution obtained by the rho. So what happens as a consequence, we have the projective dimension of that is this. And now we use again the Auslander-Buxbaum formula that Gorenstein talked about. So there's some, seems to be some method in the way the talks are designed so that it comes out to be used, right? So that's another plus for the organizers. So depth of KC is depth of KA plus depth of KB minus 1. So if A and B are Cohen-Macaulay, then I'm going to get n, which is the dimension of KC, it has to be of the n, right? Because A already has rank n, and I'm just putting A and next to it the B. I'm still going to have rank n for C. So that has to be bigger than or equal to 2n minus 1, which is not possible unless n equals 1, in which case we know everybody is Cohen-Macaulay. So when can we glue is a question. If you are saying that it cannot be glued if two things are Cohen-Macaulay, so this is one of the cases where it can glue. Supposing I have one vector, then for any integer k and k2 respectively, which are relatively prime, of course, k1 has to be relatively prime to all of these guys that appear in B, then this guy can be glued. So if B, there's only one element, so this can be glued if and only if this system, which I had, there it is, B is in the semigroup generated by A. What does this mean? This means A times X equals DB has a solution in natural numbers. That's one of the terms that you can actually glue. So this is like a quick example of that, right? So I take A, which is two guys in it, and B is 3 and 0. Oh, this has no solution because of that 0 thing, right? And therefore, this cannot be glued. But if you put them together, you can also write, this is a very small case, you can actually write the resolution just having 3 guys in it. Now, so the general case, I want to say how you do that. So let D, so you have to have a solution AX equals DB, or else you are at the sunk. So let D be the smallest positive integer such that this guy has a solution. And then while writing the proof, it turns out that I need to know what the smallest positive integer such that AX equals SB has a solution in integers and not just natural numbers. And then somehow this comes in because it comes in here, that's all. So if I take A and B, then C is a gluing if and only if these two numbers agree. That is D of AB, and then I have to take a divide out by the GCD of D and K2 unless they are relatively prime, and that has to equal the smallest positive integer as such that AX equals SB. I'll be done soon. Let me see some example. So here's an example. In fact, for some reason, this was the first example in gluing that we wrote down. So this is a case where K1 and K2, everybody is 5, because 5 times 5 and 5 is the sum of these two guys, right? 5, 0, and 0, 5. So 5B is in A. It's also the smallest positive multiple such that AX equals DB as a solution in integers as well as natural numbers. All numbers are 5, and so it's actually a gluing. So you ask why I didn't put an example. Oh, I gave an example when it is not true once, not a gluing. So here's another way of saying when you can actually glue. In fact, in some sense, for now, so far, this is the best theorem for gluing in higher dimension that we know. Suppose somebody has to have rank n, A or B. So let's say A has rank n, right? Because otherwise you will be degenerate. So A has rank n and B has rank 1. Then B can be written like this. Then it's like a numerical semigroup situation for D. So in that case, it is a gluing as long as I take K1 is relatively prime to all of those guys and K2 is relatively prime to K1. A little bit we need that K1 has to be in the numerical semigroup generated by D. So this is the closest to looking thing to Delorme's criterion. K1 is in D because D is the thing that is really there in B, and K2 is in the semigroup, relatively prime to K1. So I may have an example. So we can glue if one of them has rank 1. In general, you can't always glue. So here is the situation where if I take this to be 28, 11 plus 17, it's a gluing. But if I take it to be anything else, say somewhere else, 2, for instance, it's not a gluing. It's not because I say it's not a gluing. You can actually, because it's small numbers, you put them into Macaulay, it tells you what the number of generators are. You look at it and say, oh, it's not a gluing. Okay? So for example, this is not a gluing. I put this guy in, and this is 4. I know what this is generated by 3, and this is generated by 5. This has 27 elements instead of 9. So it's certainly very badly not a gluing. And there's so many elements that show up. So I'll just stop there. Thank you very much for listening. Mm-hmm.
Could you please go back to the slide where you state your 2018? Not all semigroup ring is of this form, right?
No, yeah, not all of them are of the form C, wherever it is, C A union B. That is right. For just the ones that can be decomposed as A and B, provided you know the resolution of A and the resolution of B.
Okay. So you have the symmetric algebra of this idea. You can easily write down the linear equations of the new set of variables defining the symmetric algebra of this idea.
Which ideal? I sub A plus I sub B. Yeah. I sub A and I sub B, if you know what they are, then you can write them.
Checking whether this symmetric algebra is torsion-free, because in this case the ideals of linear type. It means that it is bounded, for instance, by the dimension of the polynomial ring.
So yeah, this is a method you are suggesting for solving the case when C is symmetric, to see whether it is bounded. So because you're saying A is bounded, A is symmetric, and let's assume bounded by induction, and B is symmetric, let's assume, and then use that to see. I don't know, that's an idea.
Yeah. And also suppose that you have K of A is Gorenstein to make simpler, and K of B is not Gorenstein. Do you know any?
It's not Gorenstein.
Yeah, assume that K of B is not.
Yeah.
Then K of C cannot be Gorenstein.
No, definitely not.
Do you have any information about something more specific about the canonical model of this?
Yeah, because the type, you will have that from the resolution. Because you have the complete resolution, so you will have the product. Yeah, it's really going to be from the tensor product of the two things. That will show up at the end. That is going to be the canonical module, the tensor product.